Launch Director.
Launch vehicle is ready to launch.
Mission Director.
3,
You have permission
2,
to launch.
we have ignition of the RS-68A main engine, and we have liftoff of the United Launch Alliance Delta IV Heavy rocket.
Mach 1, execute. And we have indication of spacecraft separation.
At Space Launch Complex 37, a Delta IV Heavy rocket is fueled and ready to launch the NROL-44 mission for the National Reconnaissance Office. Good evening and welcome to Cape Canaveral Space Force Station in Florida. I'm Dylan Rice, a systems test engineer, launch conductor, and the host for this evening's broadcast. Liftoff is set for 8:09 p.m. Eastern Time, and the team is not working any issues. A few moments from now, at T-minus 4 minutes, the launch count will enter a planned 10-minute hold. We have 2 planned hold into today's 9.5-hour launch count. These planned holds give our team additional time to resolve any issues that come up prior to entering the terminal count. At the request of our customer, today's live coverage will conclude following payload fairing jettison, scheduled to occur about 6.5 minutes after liftoff. In addition to watching our webcast, you can follow live mission progress at ulalaunch.com. Will Ulrich, the 45th Space Wing's launch weather officer, recently briefed the weather conditions here at Cape Canaveral. Here's what we're seeing. The probability of violating launch constraints is a rare 0%. Ground winds are light and variable, and the temperature is 60 degrees Fahrenheit. So the weather is within launch commit criteria and looks favorable for our planned T0 at 8:09 p.m. Eastern Time. Today's flight will take an easterly heading away from our launch pad here at Cape Canaveral. Let's take a look at what else we can expect to see.
And liftoff of the United Launch Alliance Delta IV Heavy rocket.
At T-minus 14 seconds, the ROFIs, which look like sparklers, ignite to burn off excess hydrogen injected into the flame duct. ROFI ignition is followed by ignition of the starboard Delta IV RS-68A engine at T-minus 7 seconds. 2 seconds later, the center and port RS-68A engines ignite, generating more than 2.1 million pounds of total thrust to lift the rocket off the pad. This staggered engine start mitigates the fireball created by the hydrogen-burning Delta IV Heavy. Shortly after liftoff, Delta IV begins a pitch over to attain the proper flight path, while minimizing the pressure the vehicle experiences during flight. The Delta IV reaches Mach 1, the speed of sound, at 1 minute 18 seconds. 2 seconds later, the rocket experiences maximum dynamic pressure as it travels through Earth's atmosphere. At 3 minutes 56 seconds, the port and starboard booster engines shut down. 2 seconds later, the port and starboard boosters are jettisoned. The center booster engine then throttles to full power to maximize performance. Approaching main engine cutoff, Delta IV is traveling at more than 24,753 kilometers, or 15,381 miles per hour, is located 111 kilometers or 69 miles in altitude, and is 586 kilometers or 364 miles downrange. At 5 minutes 36 seconds, propellant levels deplete and the booster engine shuts down. 7 seconds later, the Delta IV separation system activates to release the first stage. The vehicle now weighs a little more than 5% of what it did at liftoff. At 5 minutes 56 seconds, the Delta cryogenic second stage main engine burn begins. During ascent, NROL-44 is protected inside a 5-meter diameter tri-sector payload fairing. At approximately 6 minutes 38 seconds, the payload fairing is jettisoned. Delta IV continues its national security mission following payload fairing jettison.
ULA is using the Delta IV Heavy configuration to launch the NROL-44 mission. This is the 12th Delta IV Heavy launch and ULA's 142nd mission. Built in Decatur, Alabama, Delta IV Heavy is our largest, most powerful configuration. It's comprised of 3 common booster cores, each powered by Aerojet Rocketdyne RS-68A engines, and a Delta cryogenic second stage powered by an Aerojet Rocketdyne RL-10B2 engine. Atop the rocket is a 5-meter diameter payload fairing. Launch processing events, including transporting the Delta IV Heavy from the horizontal integration facility to the mobile service tower at Slick 37, and lifting it to the vertical position using our large fixed pad erector that you can see here. Next, the spacecraft, encapsulated inside that 5-meter payload fairing, is vertically integrated to the Delta IV Heavy rocket. At approximately 10:30 a.m. this morning, the MST was rolled back to its park position. At 100 feet wide by 100 feet long by 300 feet tall, the mobile service tower is as tall as a football field is long, as wide as the length of a basketball court, and weighs about 10 million pounds. Here you can see the rotating platforms swung out in preparation for the roll to park position. The MST utilizes a carriage transporter system. It travels about a quarter mile per hour, and at that speed it takes about 25 minutes to roll the MST to its launch position 345 feet north of the launch vehicle. It's equipped with 40 hydraulic cylinders at pressures nearing 3,500 psi to raise the MST 8 inches prior to rollback. The Delta IV Heavy rocket stands 235 feet tall, or about 23 stories, and weighs about 1.6 million pounds fully fueled. The 3 engines produce more than 2 million pounds of thrust at liftoff. Today's launch is for the National Reconnaissance Office, or NRO. This is ULA's 30th launch for the NRO and the 8th use of a Delta IV Heavy for the NRO. The NRO is a joint organization engaged in the research and development, acquisition, launch, and operation of innovative overhead reconnaissance systems necessary to meet the needs of the intelligence community and the Department of Defense. The NRO is recognized for its transformational intelligence collection systems that are used to develop highly accurate military targeting data, support international peacekeeping and humanitarian relief operations, and to assess the impact of natural disasters. As they do for every mission, the NRO provided unique artwork for NROL-44. Here's the story behind the art. The background of this artwork is a dark shade of NRO blue to symbolize cross-organization collaboration required for mission success. In the foreground, we see a wolf howling as a warning to its pack as the first point of detection for signs of trouble. The wolf pack represents the nation and the international community leveraging and supporting the steadfast sentry. Lastly, the falling snow represents the purity of the NRO's intentions and the serene calm of peace. This is the 12th flight of the Delta IV Heavy. Let's take a look back at this impressive rocket. With 3 booster cores generating more than 2 million total pounds of thrust off the pad, the imposing Delta IV Heavy rocket is the nation's proven heavy lifter. Add in its high-performing Delta cryogenic second stage, and the Heavy delivers the flexibility and agility for the most demanding missions, like NASA's Parker Solar Probe launched in 2018. Launching from both Cape Canaveral and Vandenberg Air Force Base in California, ULA's Delta IV Heavy has an impressive resume.
Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-46 mission for the National Reconnaissance Office. Carrying the NROL-32 mission for the National Reconnaissance Office.
And liftoff of the United Launch Alliance Delta IV Heavy, carrying the NROL-15 mission for the National Reconnaissance Office.
Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-65 mission for the National Reconnaissance Office.
At dawn, the dawn of Orion, and a new era of American space exploration.
Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-37 mission for the National Reconnaissance Office.
Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe.
Liftoff of the United Launch Alliance Delta IV Heavy rocket with NROL-71.
A few moments ago, Mission Director Colonel Chad Davis remembered our friends and colleagues Chuck Mitchell, Mark Wright, and Winnie Pang. Let's listen in.
This evening's NROL-44 launch is dedicated to the memory of Chuck Mitchell and Winnie Pang. Chuck and Winnie have dedicated countless hours of technical expertise, ensuring the incredible success of a multitude of launches. Their warm smiles, team spirit, and phenomenal leadership have rippled across the aerospace and launch communities. To our fellow patriots, rest in peace.
NROL-44 is also dedicated in memory of ULA employee Mark Wright. Mark spent most of his life on the Space Coast and loved all that it represented. He began his career at Boeing working on multiple space programs before joining the Delta IV team in 2001. As a quality inspector, Mark was instrumental in preparing Slick 37 for its first Delta IV launch in 2002 and helping to ensure mission success at all ULA launch pads. Mark earned the respect of all who knew and worked with him, and he will always be remembered for his unwavering honesty, positive attitude, strong work ethic, big heart, and friendly smile.
918. RLM 918. Elsie concurs. RLM Elsie.
T-minus 8 minutes.
RLM, go ahead. Disable line item 918. In work. OSM Elsie.
This OSM.
Place the SRM ignition to enable.
SRM ignition enable. To enable.
GE, verify TISR status ready.
Roger. TISR status ready.
SYS, establish best source selector, locked on RF and range sources.
Roger.
Initiate orbital parameter calculations on primary CCLS.
Roger.
And SYS, did you get your primary balloon cycle test complete?
Yes, I reported that complete.
Roger.
LCRLM on 1.
Go.
Delta rockets have launched many of the world's vital space assets. Let's take a look at the impressive legacy of the Delta family of rockets.
Though first launched in 1960, Delta's story really begins in the mid-1950s with the development of the Thor Intermediate-Range Ballistic Missile. Named after the Norse god of thunder, Thor was created in response to a growing fear that the Soviet Union would beat the US in the deployment of a long-range ballistic missile. The goal was to design a system that could deliver a nuclear warhead to a target 2,300 miles away, the distance between the United Kingdom and Moscow. On January 25, 1957, the first Thor lifted off from the newly constructed Space Launch Complex 17 at Cape Canaveral. Following a series of early failures, the Thor team celebrated their first success on September 20, 1957. In all, 59 Thor IRBMs were launched, with the last flight occurring in 1975. Thor began the transition from missile to space launch vehicle in 1958. On October 11, 1958, America's newly formed space agency marked its inaugural launch when Thor Able boosted NASA's Pioneer 1 on a mission to the moon, and NASA's long partnership with Thor was born. NASA and the Douglas Aircraft Company began development of the fourth and longest-lasting Thor configuration in April 1959. Using a Thor first stage and a Vanguard second and third stage, Delta I lifted off on May 13, 1960 from Cape Canaveral Space Launch Complex 17. Though its first launch was not successful, the Delta team quickly pinpointed the failure and 3 months later delivered NASA's Echo 1 communication satellite to orbit. Following Echo 1, the Delta team racked up an impressive 22 successful launches. Led by Bill Schindler, the Delta rocket earned its industry workhorse moniker for rapidly establishing itself as one of the most reliable and versatile launchers. During the 1960s, Delta launch vehicles paved the way for the burgeoning communications industry, launched America's first weather satellites, and sent probes to explore our universe. AT&T's Telstar 1, the first commercial communications satellite, launched in 1962, and in 1963, SYNCOM-2 became the world's first geosynchronous satellite. TIROS, or Television Infrared Observation Satellites, provided the National Weather Service with humans' first view of the Earth's cloud cover. In orbit around the Earth, Moon, and Sun, NASA's Explorer satellites provided us with a deeper understanding of the solar wind, cosmic rays, as well as Earth's magnetic field and radiation belts. By the end of the decade, launch vehicle modifications, including the addition of solid rocket motors and an upgraded third stage, made it possible for Delta to orbit satellites 10 times larger. The 1970s was an international decade for Delta, as the manifest included scientific and communication satellites for several countries across North America, Europe, and Asia. Perhaps the most demanding challenge of the 1970s was the launch of the Earth Imaging Earth Resources Technology Satellite, later known as Landsat. The mission for the Earth Sciences community required major changes to the Delta propulsion and guidance systems. During the 1980s, Delta continued its reliable service to the communications, weather, and Earth imaging communities. As capable as the Delta rocket proved to be, production came to a halt in the early 80s when national space policy dictated that the space shuttle be used as the U.S.'s primary launcher, signaling the end of the expendable launch vehicle. But in 1987, the Delta team picked up where they left off, and development began on a launch vehicle to support the Air Force's Global Positioning System. On February 14, 1989, Delta 184 began a new chapter in space launch history as it lifted off from Space Launch Complex 17, demonstrating an incredible feat. The Delta II had gone from development to launch in just 2 years. To accommodate the larger GPS satellites, engineers improved the Delta rocket in several ways. The fuel tanks were stretched, a new payload fairing was developed, and larger solid rocket motors were incorporated. The modifications resulted in increased performance and flexibility. By the mid-1990s, the Delta II had delivered the fully operational In partnership with the Air Force's evolved Expendable Launch Vehicle program, the Delta team began development of the next generation Delta rocket in the mid-1990s.
And we have liftoff of the first Boeing Delta IV rocket carrying the W5 telecommunications satellite for Eutelsat of France.
All Delta IV configurations begin with the Common Booster Core, powered by the RS-68A main engine. The Delta IV Heavy, with its 3 common booster cores, deliver our nation's largest missions to orbit.
Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-44 mission for the National Reconnaissance Office.
Delta IV launch vehicles are produced at a 1.5 million square foot state-of-the-art facility in Decatur, Alabama. Processing and launch takes place at Space Launch Complex 37 at Cape Canaveral Air Force Station and Space Launch Complex 6 at Vandenberg Air Force Base in California.
Range safety arm light on. Right. Range ready. Ready. Water system ready.
From its early beginnings as a weapon and deterrent through its transformation into a space launch vehicle, Delta has reliably supported our nation for more than 60 years. Delta's legacy as a workhorse continues today and is a testament to the persistence, dedication, and commitment of an enterprising team that has continually evolved the Delta rocket to support a changing world.
5, 4, 3, 1, and liftoff of the United Launch Alliance Delta IV Heavy rocket.
Loud and clear. Loud and clear as well. ATD.
Loud and clear.
Loud and clear as well.
Launch on time verified.
Roger. LC switch to the ready position. All steps are complete prior to the status check.
This is Delta Mission Control. We have entered the planned 10-minute built-in hold, and preparations for launch continue. In a few moments, Launch Conductor Scott Barney will poll the launch team for the final go to pick up the count. 27 engineers and managers are polled for system status and readiness to proceed. This is the final status check before launch for all Delta vehicle systems, ground systems, the spacecraft, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Scott Barney performs the final polling of the launch team.
Status check to proceed with terminal count. First stage systems, propulsion. Go. Hydraulics. Go. Box.
Go.
LH2.
Go.
Second stage system locks.
Go.
LH2.
Go.
Electrical systems airborne. Go. Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
COM.
Go.
GCQ.
Go.
Operations support.
Go.
Pneumatics. Go. Umbilicals. Go. ASGAS.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicles ready to launch.
L minus 6 minutes.
Mission director.
You have permission to launch.
Proceeding with the count. MEQ establish swing arm. Lock pins pulled.
Active.
Polling is complete, and the launch team has given the go for launch. The countdown will resume approximately 2 minutes from now, but before it does, let's walk through the final checks we'll hear from the launch team. At T-minus 4 minutes, and counting, the team will enter the terminal count and begin securing the second stage liquid oxygen tank. At T-minus 3 minutes 32 seconds, booster liquid hydrogen and liquid oxygen tank securing is started, which includes closing the propellant fill and drain valves. Also at T-minus 3 minutes 32 seconds, vehicle transfer from ground facility power to its own internal battery power will be complete. At T-minus 3 minutes, the vehicle ordnance system is armed and booster liquid oxygen and liquid hydrogen propellant tanks are verified to be at flight pressure and flight level. 2 minutes prior to liftoff, the team will verify that the hydraulic system is pressurized, as well as confirm booster, second stage, and flight termination system battery voltages. At T-minus 120, the team will begin securing the second stage liquid hydrogen tank. At T-minus 60 seconds, the Eastern Range readiness is verified. At T-minus 50 seconds, the second stage liquid hydrogen tank is secured at flight level. A final launch vehicle and spacecraft status check is conducted at T-minus 30 seconds. At T-minus 15 seconds, the ROFIs, or sparklers, are ignited to burn off excess hydrogen at the base of the vehicle. At T-minus 7 seconds, the starboard engine ignites, followed by the core and port engines. Liftoff will occur at T0. After liftoff, you'll hear the voice of Patrick Moore providing launch vehicle ascent data. Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
T-minus 4 minutes and counting.
The countdown clock has resumed. We've entered the terminal count and are go
3:55.
for launch at 8:09 p.m. Eastern.
Ground pyros enabled.
$325.
Second stage lock, secure at flight level.
$307. T-minus 2 minutes, 49 seconds.
FTS internal.
CBC locks at flight pressure and flight level. CBC LH2 at flight pressure and flight level.
With that call, the first stage tanks are now ready for flight.
T-minus 2 minutes, 159.
Vehicle internal. Hydraulic pressure at 4,000.
155.
Launch sequencer start.
$140.
FCS launch enable.
$137.
T-minus 90 seconds.
FCS armed.
The launch vehicle, payload, ground systems, and Eastern Range are go for launch.
$120.
FCS count started. OCUs armed.
T-minus 1 minute.
Engine start box go. Rock, report range status.
Range green.
$50 seconds.
Second stage LH2 secure at flight level.
30 seconds.
Status check.
Go Delta.
Go NROL-44.
$15 seconds.
Roll for ignition.
T-minus 10,
10.
9, 8, 7, 6, 5. Main engine ignition. 3, 2, 1, 0, and liftoff. Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-44 mission for the National Reconnaissance Office.
On all three R68A engines look good in full thrust mode. Now 15 seconds into flight, vehicle's begun the pitch over maneuver. Body rate response look good.
You are hearing the voice of Patrick Moore providing launch vehicle asset data.
25 seconds into flight, engine operating parameters continue to look good. Body rate responses look good. Now 30 seconds in. Standing by for core booster throttle down momentarily. And core booster has begun throttling down as expected. The partial thrust level engine response looks good. Core booster has achieved partial thrust level as expected. Now 50 seconds into flight. Engine operating parameters continue to look good on all three engines. passing 1 minute into flight. Delta IV is now 4.3 miles in altitude, 5.8 miles downrange distance, traveling at 1,200 miles per hour. And at 1 minute 20 seconds into flight, vehicle is now passing through max Q, maximum dynamic pressure. Vehicle is also passing Mach 1. Delta IV is now supersonic. Engine operating parameters continue to look good on all three boosters. Port and starboard booster in the full thrust mode, core booster in the partial thrust mode. Body rates continue to look stable throughout the boost phase of flight. Telemetry quality has looked good throughout the boost phase. Now passing 1 minute 46 seconds into flight. And the second stage reaction control system is pressurizing to flight levels. System response looks good. Engine operating parameters on all three engines continue to look good. Body rates continue to look stable. Vehicle has now gone to closed loop guidance. Seeing some correction in the attitude as expected when vehicle switches over to closed loop guidance. Now 2 minutes 37 seconds into flight, approximately 3 minutes remaining in boost phase of flight. And the Delta IV rocket now weighs just 1/2 of what it did at liftoff, burning propellant at a rate of almost 5,000 pounds per second. Body rates in roll, pitch, and yaw have nulled out nicely now after the closed loop guidance switchover. And vehicle is now passing Mach 5. Engine operating parameters continue to look good. Port and starboard boosters in the full thrust mode, core booster in the partial thrust mode. Vehicle body rates have damped out nicely now as the vehicle is continuing in the latter part of the boost phase. Approximately 30 seconds now remaining until port and starboard booster engines cut off. And approximately 2 minutes now remaining in the boost phase of flight. And standing by for strap-on engines throttle down. And strap-on engines have begun throttling down in preparation for engine cutoff. And port and starboard booster engines have cut off. And we've seen good indication of separation of the port and starboard boosters. Core booster is throttled back up to full thrust as expected. Engine response looks good. Now 4 minutes, 20 seconds into flight. And the upper stage liquid oxygen system has begun boost phase chill down sequence to begin thermal conditioning of the RL-10 engine. And approximately 1 minute now remaining until BECO. And upper stage fuel system has now begun boost phase chill down. Core engine continuing to look good in the full thrust mode. Engine operating parameters look nominal. Now passing 5 minutes into flight. And the Delta IV is now 71 miles in altitude, 360 miles downrange distance, traveling at 12,900 miles per hour. And approximately 10 seconds until core booster throttle down. And core boosters begun throttling down in preparation for BECO, standing by for BECO. And we have BECO, booster engine cutoff, standing by for stage separation. And we have good indication of separation of the first and second stages. Nozzle extension on the RL-10 is deploying. We have pre-start. We have ignition and full thrust on the RL-10. Chamber pressure on the RL-10 looks good. Body rate responses look good on the DCSS. Now passing 6 minutes, 15 seconds into flight. Engine operating parameters continue to look good on the RL-10. Upper stage has begun initial thruster firings to begin catalyst bed warming. Seeing a couple of periodic dropouts in telemetry. And we have seen good indication of payload fairing jettison.
As you just heard with that call for payload fairing jettison, that will wrap up this evening's live coverage of the broadcast. ULA's Delta IV Heavy made history this year when it became the first operational rocket to host 3D projection mapping. Let's take a look at the footage from this unique event.
I'm Tori Bruno, President and CEO of United Launch Alliance. You are about to see the first ever 3D animated projection on an operational rocket. And of course, we have chosen the majestic Delta IV space launch vehicle for this experience. So enjoy the show and God bless America.
We are dreamers, inspired by possibilities not yet imagined. Believers driven to harness the potential of space. Leaders combining expertise and ingenuity. And it all started with a spark of the imagination.
Go. SYS. Go. DSE. Go. Timer. Go. ECS. Go. QE. Go. USO. Go. OSM. Go. BSE. BSE is go. ALC. Go. AC. AC is go. RC. Clear to proceed. Launch Director. The launch vehicle is ready to launch. Mission Director. You have permission to launch.
10, 9, 8, 7, 6, 5, 4. Main engine ignition. 2, 1, and liftoff. Liftoff of the United Launch Alliance Delta Heavy rocket.
Although ULA's focus is on the future, we will always celebrate our incredible legacy. 140 missions, 140 successes, enabling our customers to save lives, explore the universe, and connect the world. From John Glenn, the first American to orbit the Earth, to new ways of connecting the world. From the most accurate weather satellites ever deployed.
Mandatory evacuation for Central Florida.
To game-changing national security satellites. And launching missions throughout the solar system and beyond. to once again sending astronauts to space from U.S. soil. And doubling down on our commitment to our country. America has always and will always be at the forefront of space. This mission is no different. As we prepare to launch another critical asset to protect our way of life. The National Reconnaissance Office. When our country needs eyes and ears from the high ground of space, to give advanced warning to threats, to aid in the aftermath of natural disasters, to answer our most pressing intelligence questions. It turns to the National Reconnaissance Office. The leader in national space intelligence systems. Over the next decade, ULA will continue to protect life on Earth with the introduction of the Vulcan Centaur. Our next generation rocket. A rocket purpose-built for national security. Founded on the Atlas and Delta legacy of success. With Vulcan Centaur, we are engineering limitless possibilities for a safer, more secure existence at home and in space. We are dreamers, inspired by possibilities not yet imagined. Believers, driven to broaden horizons. We deliver progress above.
This is Delta Mission Control at T plus 14 minutes 40 seconds. I hope you enjoyed the shows, the 3D video projection, and the successful liftoff of the Delta IV Heavy rocket carrying the NROL-44 mission. Liftoff occurred at 8:09 p.m. Eastern Time. At our customer's request, we'll now terminate our live coverage. I'd like to thank Patrick Moore for his participation in this evening's broadcast. For more information, follow us on Facebook or Twitter or our blog at ulalaunch.com. We'll leave you now with another look at the liftoff of the Delta IV Heavy rocket this evening. I'm Dylan Rice, and on behalf of the entire launch team, thank you for joining us and have a great evening. 8, 7, 6, 5, main engine ignition, 3, 2, 1, 0, and liftoff. Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-44 mission for the National Reconnaissance Office.
On all three RS-68A engines look good in the full thrust mode. Now 15 seconds into flight, vehicles begun the pitch over maneuver. Body rate responses look good.
You are hearing the voice of Patrick Moore providing launch vehicle ascent data.
25 seconds into flight, engine operating parameters continue to look good. Body rate responses look good. Now 30 seconds in. Standing by for core booster throttle down momentarily.
Hi, it's me, Tim Dodd, the Everyday Astronaut. As most of you probably know, we're witnessing the biggest, most powerful, most ambitious rocket ever built come to life before our eyes. Yes, of course, we're talking about SpaceX's Starship. This thing is the ultimate challenge in aerospace engineering. It's a fully and rapidly reusable super heavy lift launch vehicle capable of taking around 150 metric tons to low Earth orbit. And yes, that is more payload than the Saturn V, and don't forget it does that while being fully reusable. But Starship's ultimate purpose goes way beyond just terrestrial orbital ambitions. Starship is the first vehicle really designed to actually take human beings to Mars and bring them back again. In order to achieve this absolutely bonkers goal, SpaceX has had to employ a litany of new technologies, use new materials, develop the most advanced rocket engines ever made, and come up with some really wild ideas that have never really been tried before, and perhaps for a good reason. So today, let's go over all of these new technologies and compare it to SpaceX's Falcon 9 and Falcon Heavy to help point out what things are new, what things are different, and what they've learned from the Falcon family that will apply to Starship in order to really understand just how ambitious this project is. But we're not just going to be scratching the surface here. Oh no. In fact, we're actually going to be taking you inside the rockets and showing you basically every single part and going over all the systems with a fine-tooth comb so that you can learn as much as possible. So that means there's a ton to cover. And because Starship's evolution is finally slowing down just a little bit, this can be your definitive guide to Starship. For now. Let's get started.
3, 2, 1,
That's one small step for man.
Contact with a test 1.
Now, right off the top here, before we get started, I just wanted to quick point out our awesome Future Martian Society t-shirt that I'm wearing that has lots of awesome little nods to Starship. You can find out more at everydayastronaut.com/shop. Okay, watching Starship come to life sure is addictive. The general public has never had access to a rocket's development like this before. I just love watching all the updates roll in from Elon Musk's Twitter, but also from Mary and the NASA spaceflight crew, S Padre, Lab Padre, RGV Ariel, and Oscar Bernard. I mean, every single day there's some awesome content out there. I don't really seem to recall a time when any company started building a product before they really had a factory, and then they just started building a factory around the product. I guess Boca Chica is just kind of backwards like that. Now, right off the top here, I want to teach you guys one thing that's confusing. Starship is the name of both the entire rocket as a whole and also just the upper stage. They're both Starship. But Super Heavy is the first stage or the booster of the entire Starship system. So yes, it's confusing, but you'll hear me say Starship kind of meaning the whole system, but I might also be meaning just the upper stage. So just listen for context. We should also point out here that Starship is a potential fleet of different vehicles. You might want to call it the Starship Launch System, or SLS. Wait, that's a thing. Generally speaking, in today's video, we'll be talking about a generic crew version, which we often see in the renders. But there's also a cargo version with a cargo bay that opens its jaws like an alligator and releases massive, massive payloads. And there'll also be a tanker variant that only carries some additional propellant as its payload in order to refuel other starships already in orbit. And we may someday see one-way bound starships that are stripped down and only made to inject payloads to the outer solar system. And there's also going to be that lunar lander version, which will only stay in space in the Earth-Moon system and won't have the large flaps or heat shields, and will also have additional landing engines so they don't end up kicking up too much lunar regolith. Well, and then don't forget about the point-to-point version. That might be a different iteration that's just for Earth-to-Earth transportation. There could be just a whole new type of vehicle called Starship, and this is literally just the beginning of that. So all this is to say, Starship is still a bit in its development phase, but it is truly solidifying and maturing to the point where we can actually put all of this together for you. But do note, things might change. Okay, so this is gonna be a long video, and like all my long videos, here's the timestamps, which we also have in the description, and the YouTube play bar is broken up as well. There's also an article version for easy reading and searching at everydayastronaut.com. So before we start, we might want to lay out what's the same between the Falcon 9 and Starship, because that might be an easier place to start. What's the same? Well, they're both rockets. We can start there. Both rockets have 2 stages. They both run on super chilled liquid fuels and have a reusable first stage with legs and grid fins. They're both made by SpaceX. They probably have virtually the same avionics and software. I think that's about it. Oh, they each have a bunch of engines. There we go. But I think that's literally it. I guess it's no wonder they stopped calling it the BFR or Big Falcon Rocket, because Starship really has almost no Falcon heritage anymore. Okay, next. Where to begin? Well, for starters, quite literally, the heart of each rocket is its rocket engine, or in this case, rocket engines. Because the Falcon 9, as the name suggests, uses 9 Merlin 1D engines on the first stage and a single vacuum-optimized Merlin called the MVac on the second stage. The Merlin engines are open cycle, meaning that they have a small baby rocket engine called a gas generator that burns just a little bit of fuel and a dash of LOX, and then that high energy exhaust hits a turbine, and that turbine then spins the main propellant pumps. The exhaust from that process is simply dumped overboard, like on the sea level Merlin, but on the vacuum Merlin, they actually route that exhaust gas back into the nozzle to help provide a layer of cooler gas to keep the nozzle extension from melting. That's still crazy to me. But SpaceX took everything to 11 when they decided to take on the most ambitious rocket engine ever made. They developed an engine called the Raptor engine, which is a full-flow staged combustion cycle engine. The reason it's so complicated is all of the exhaust gas that would normally be dumped overboard after spinning the turbine is instead routed back into the main combustion chamber. But not only that, there's 2 of those little rocket engines and 2 turbines and 2 pumps, and then both of their exhausts are pumped into the main combustion chamber. One of those is fuel rich and the other is oxygen rich. One little note here, if an engine is closed cycle where that exhaust gas is routed into the combustion chamber, we will call the gas generator a pre-burner instead, since it's just pre-burning the fuel or the oxidizer, or both, and it's then routed straight into the combustion chamber. Despite extremely hot gaseous oxygen wanting to turn every bit of the engine into soup, having the fuel and the oxygen arrive in the combustion chamber as a hot gas adds a huge boost in efficiency. Or as Elon would say,
certainly 98.5%, hopefully 99% of theoretical combustion efficiency. This is so if God himself came and knitted together the molecules to do 1% better. Okay, maybe 1.5% better. That's very high efficiency.
Because of full flow stage combustion.
Full flow stage combustion, exactly.
This engine is so advanced that there's only ever been 2 other attempts at building one ever. Neither of those engines would ever leave the test stand and fly.
Yes! Oh my God, it's actually flying!
And as of the making of this video, the Raptor has powered 4 short hops. Despite them never exceeding 150 meters, it is the only time in history a full-flow staged combustion cycle engine has been used to perform work. But these hops were relatively simple. Only a single engine, sometimes offset from the center of the rocket, like the prototype Seal number 5 and Seal number 6. But 3 engines is next for Starship for its first true flight, planning to reach 15 kilometers to practice its crazy landing sequence. From there on out, the number of Raptors Starship will utilize will just keep on increasing. The orbital version of Starship will have 3 sea-level Raptors and 3 large vacuum-optimized Raptors, which are currently in development and beginning their testing, which is really exciting. The Super Heavy booster will end up with over 24 engines, eventually getting up to over 30 engines probably. Now this is all because of their relatively small size. SpaceX can squeeze tons of these Raptor engines on the bottom of the large rocket. And don't worry, Starship shouldn't suffer from N1 syndrome. People sometimes are quick to point out how using so many engines on the first stage is dumb because the Soviet Union's N1 moon rocket developed in the 1960s failed on all 4 of its launch attempts. Well, first off, don't forget the Falcon Heavy has had a perfect flight record, and that thing uses 27 engines, so clearly the number of engines doesn't scare SpaceX. But also, the N1 failed for many reasons, all of them really having very little to do with the actual number of engines. In fact, having multiple engines is considered an advantage for the Falcon 9 and Falcon Heavy because it allows for engine out capability. Now, this is proven useful on 2 flights where an engine has shut down on ascent, but the mission was still successful, something that fewer engined rockets might not be able to do. While we're talking about engines, we should mention the fuels each rocket runs on. The Falcon 9 runs on rocket-grade kerosene known as RP-1, along with liquid oxygen. The combination is often referred to as Kerolox. Starship and its Raptor engines run on liquid methane and liquid oxygen, otherwise known as Methalox. Liquid methane burns cleaner than RP-1, leaving behind virtually no soot in the engine. It also has the potential to be more efficient, but it is less dense than RP-1, which leads to slightly larger tanks by volume. One thing unique to SpaceX is in the constant pursuit of performance, they began utilizing super chilled propellants on the Falcon 9 in 2015 with their first full thrust Falcon 9. This means that they chill the RP-1 and the liquid oxygen more than any other operational rocket. SpaceX chills their RP-1 from pretty much ambient temperature down about 30 degrees Celsius, so it ends up being below zero. Brr, but now that's nothing compared to the liquid oxygen. SpaceX chills the liquid oxygen all the way down to minus 207 degrees Celsius, which is only 12 degrees away from freezing solid. Although they haven't likely gotten too far into super chilling propellants for the Raptor engine, it is in the works. But by default, liquid methane is very close in temperature to liquid oxygen. Its boiling point is minus 161.5 degrees Celsius, and it becomes a solid at minus 182 degrees Celsius. So we'll likely see SpaceX chill their methane down closer to minus 180 degrees Celsius as the engine develops and as they continue to squeeze performance out of that beast. Now, if you need to know all about the full flow stage combustion cycle and other cycles, and why they use methane, be sure and watch my video all about the Raptor engine so you can understand the cycle better and the trade-offs of using methane. But there's more than just a fuel and oxidizer tank inside each stage of these rockets. And here's where the Falcon 9 is more complex than Starship because it has 3 additional consumables on board stored inside smaller tanks. Inside each oxygen tank of the Falcon 9 is a set of composite overwrapped pressure vessels, or COPVs, that house compressed helium. And when I say compressed helium, I mean compressed. We're talking 380 plus bar in these bottles. They use these to maintain constant pressure in the propellant tanks of about 3 to 4 bar. So as the fuel drains out, they put helium in its place, which is extremely undense, or not dense. And that ends up filling the void and maintains sufficient pressure, and it's inert, so it's not explosive. Starship might eventually do away with these almost entirely. They'll likely always need some COPVs to store helium to spin start the Raptors, but SpaceX will be utilizing something called autogenous pressurization of the propellant tanks. While the engines are running, they'll be pumping some higher pressure fuel or oxidizer back into their respective tanks to maintain proper pressure. The space shuttle did the same thing. But once they're in space, they're going to maintain their pressure by allowing some of the fuel to boil off, and then release any excess pressure. And of course, temperature and pressure are directly related due to the laws of thermodynamics, so by releasing pressure, it also helps maintain their temperature. And they can store propellant in smaller tanks, which are inside the main tanks, and these are called header tanks. Since they're going to be inside of another tank, the propellant will receive almost no heat from the sun, and therefore it shouldn't boil off. But there's another reason for those header tanks. They're kind of reserve tanks in a sense, mostly for the landing phase. We'll talk about this more in a minute, but Starship will do some pretty intense maneuvers, and if it tried to light its engines from a partially empty tank, it would suck up air bubbles, which would destroy the engine. So these header tanks just provide a source of propellant that's on tap, no matter the orientation or G-load of the rocket. But one interesting thing about Starship is its tanks will be at a higher pressure overall than the Falcon 9. They'll maintain more like 5 or 6 bar instead of 3 or 4. Isn't it honestly super weird to think that when a rocket like the Falcon 9 is fully fueled up and pressurized for flight, there's more pressure inside of that rocket than a car tire? And Starship will have almost twice as much pressure as that when it's pressed for flight. That's honestly just crazy to me. Another thing the Falcon 9 has that Starship won't have is ignition fluid. The Falcon 9 uses what's known as TTEB, or triethyl aluminum triethyl borine, which is a pyrophoric mixture. This means it'll instantly combust when it comes in contact with oxygen. As SpaceX gets the pumps spinning up on the Falcon 9, they inject TTEB into the combustion chamber to initiate combustion while they begin to dump fuel and then get it into a stable combustion state. This is important to be able to restart the Merlin engines with an onboard starting fluid so they can relight some of the engines 2 or 3 times during its reentry and landing process. Now, without TTEB, the engines would fail to reignite. If you look closely before any Merlin engine ignition, you might actually catch the green flash from the TTEB. And again, just like with helium, you can't exactly refill your TTEB bottles on Mars. So for Starship and Raptor engines, they're utilizing a spark ignition. I think this is quite literally like a giant spark plug, or basically a freaking arc welder that begins the ignition process. But there's one more propellant SpaceX uses on the Falcon 9, and that's cold gas or compressed nitrogen. Basically just compressed air, since nitrogen is 78% of the air we breathe. They utilize compressed nitrogen for the cold gas thrusters on the inner stage of Falcon 9, the part between the first and second stage. There's 2 packs of 4 little thrusters sitting way up there on top of the booster. These are there to help it flip around and continue to point and guide the booster as it coasts before re-entry. And just like before, there's not as much nitrogen on Mars, but even more so, SpaceX doesn't want to have to carry around a separate propellant if they don't really have to. So instead, Starship will actually utilize brand new hot gas thrusters that are powered by gaseous methane and gaseous oxygen. We don't really know too much about these new thrusters, but knowing SpaceX, they'll probably be named after a bird. So all in all, the different fuels, different cycle types, different sizes, and all other considerations leads to pretty drastic upgrades in performance for the power plant of each rocket. SpaceX's Merlin engine reaches an impressive amount of thrust at 845 kilonewtons at sea level and 981 kilonewtons in a vacuum. But the Raptor engine is currently in its infancy and running at around 1650 kilonewtons at sea level and can achieve probably somewhere around 1800 kilonewtons in a vacuum. But they've already achieved just above 2000 kilonewtons of thrust on the stand, and that will be their operating thrust relatively soon. And there's another more powerful variant coming. Someday there's going to be a non-deep throttling booster variant of Raptor that'll be on the outer ring of the booster. And they're targeting closer to 3000 kilonewtons of thrust at sea level and more like 3200 kilonewtons of thrust in a vacuum. Wow. I mean, after all, the Merlin has had every single last drop of performance squeezed out of it after over a decade of continuously developing the engine, and the Raptor is just in its infancy. Next up, efficiency. Now this is measured in specific impulse, or ISP. The higher the number, the better, kind of like the gas mileage or fuel efficiency of a car. The Merlin is pretty darn efficient, achieving 282 seconds of specific impulse at sea level and 311 seconds in a vacuum. But the Raptor engine is even more efficient, currently achieving 325 seconds at sea level and close to 350 seconds in a vacuum. A lot of this performance is due to the chamber pressure inside the main combustion chamber. The higher the chamber pressure, the more potential the rocket has to turn that high pressure into higher thrust and better efficiency too. The Merlin achieves 116 bar of pressure, while the Raptor is operationally at around 275 bar currently, but it's hit 330 bar on the test stand, and it will likely reach their goal of 350 bar operationally before too long, knowing SpaceX. But at the end of the day, there is one metric where Merlin currently outperforms the Raptor. That's thrust to weight ratio. the Merlin will be hard to beat because it has the highest thrust-to-weight ratio of any liquid-fueled rocket engine ever. The Merlin engine has a nutty thrust-to-weight ratio of around 200 to 1, while the Raptor currently is around 107 to 1, but increasing to 130 to 1. And again, Elon thinks they can get it to match the Merlin someday. But perhaps one metric that's just as important, especially when you're cramming dozens of engines inside of a fixed area, is thrust to engine footprint ratio. You may notice that the Raptor isn't that much wider or take up that much more space than the Merlin. And especially when you factor in the entire footprint of the engine. Notice that the Merlin has that large gas generator exhaust just sticking way off on the side of the engine, while the Raptor almost fits inside its own footprint. This stuff matters when you're cramming tons of engines together. So when it's all said and done, the first stage of the Falcon 9 with its 9 engines achieves 7.6 meganewtons of thrust. Falcon Heavy, which is currently the most powerful rocket flying, gets 22.8 meganewtons, and Starship's Super Heavy booster will end up with, ready for this, about 3 times the thrust of that at 65 meganewtons. That's likely going to be about the minimum thrust we'll see for an operational orbital version, but it'll probably increase when they start utilizing more engines or those more powerful booster variants on the outer ring. Okay, I know what you might be thinking right now. Why didn't they just put the Raptor engine and test it out on the Falcon 9? Could they? Technically, maybe yes, and it was kind of looked at for an upper stage variant for a Falcon Heavy, but really by the time you do that, it wouldn't be worth it at all. If you were to put, say, just a Raptor engine as an upper stage for Falcon 9 or Falcon Heavy, you'd have to redesign the whole upper stage because now it has to handle a lot higher loads because don't forget, it's over twice as powerful. The Merlin vacuum engine is already too powerful and it has to throttle way down to be able to not smash all of its things it's trying to put up into space. And of course, you couldn't put 9 Raptor engines inside the same diameter of a Falcon 9 because they wouldn't fit. So you could maybe do like 3 or 4, but now you don't have a good way to have a landing engine. Your forces are totally different. Your bulkheads are different because of the different densities of fuel. All of this, it would be a totally different rocket. And if you're building a new rocket anyway, why not go big? Well, they did that exact same thing with the Falcon 1. People thought it was crazy. They weren't just upgrading their Falcon 1 and flying it more, and that they were going to be jumping to the Falcon 9. But in hindsight, it's a really good thing they didn't sink $1 more into the Falcon 1, and it's a good thing they moved on to a bigger and better rocket, the Falcon 9. And now, SpaceX is doing this all over again. And if you're starting over with a totally fresh design, you might as well go bigger. I mean, a lot bigger. Okay, next, their sizes. Starship is massive. Like, really, really big. Now don't get me wrong, the Falcon 9 is actually quite a decent sized rocket, and it's really hard to appreciate just how big it actually is until you're standing underneath it. But at 9 meters wide compared to the Falcon 9's 3.7 meters wide, the Falcon 9 is narrow enough to be transported cross-country by road. But Starship, not so much. Although it does get transported by road, it only does a little tiny bit on a completely closed off highway in Boca Chica, Texas. The Falcon 9 stands 70 meters tall, with its first stage at 45 meters tall, while the second stage and the nose cone, or fairing as we call it, comprise the other 25 meters. Despite being pretty tall, the entire Falcon 9 will be able to fit inside just the Super Heavy booster. The Super Heavy booster will stand over 72 meters tall, likely closer to 75 meters tall. Then put the Starship upper stage on top of the Super Heavy booster, and the entire stack will stand 122 meters tall. That's over 10 meters taller than the monster Saturn V. Yep, that's right. It'll be about as tall as a 35-story building. In fact, it'll pretty much be exactly as tall as the tallest skyscraper-esque condominiums on nearby South Padre Island, the Sapphire South Padre, which stands 123 meters tall. And once you put Starship up on its massive launch mount, it'll be the tallest thing for hundreds of kilometers. Yeah, just wait until that thing takes off. I think it's going to melt a few brains and probably break a few windows. Couple this massive size with their different engines with different performance figures and different fuels, and what it all means is Starship can put a lot bigger and heavier things into orbit. The Falcon 9 can take 22,800 kilograms into low Earth orbit when it's expended, or 15,600 kilograms when reused, like it does for the Starlink missions. It can send 8,300 kilograms on a geostationary transfer orbit when expended, or around 7,000 kilograms when reused. Now let's drop in Falcon Heavy, which can take between 63,800 kilograms when fully expended, and about 27,500 kilograms with 2 cores returning to the launch site and 1 core landing on the drone ship. Falcon Heavy can even get about 25,000 kilograms to geostationary transfer orbit when fully expended, but it still gets about 9,500 kilograms when doing the 2 core on land, 1 core on the drone ship. But Starship will be able to take over 150,000 kilograms to low Earth orbit. Yeah, that'll be more payload mass than any rocket ever made, even beating out the Saturn V, which could only put 145,000 kilograms into low Earth orbit. Starship can also put a solid 21,000 kilograms out to a geostationary transfer orbit, despite having to lug its own huge dry mass around there. So yes, it's lower than an expendable Falcon Heavy, which is over $100 million, but if you expended a super heavy booster, it would easily exceed that. But expending a super heavy booster is just simply not in the plans. Don't forget, since the whole rocket is reusable, Starship has to take its heavy flaps, landing gear, the payload fairing, and all 6 engines with it everywhere it goes. So instead, here's where Starship can make up for that with orbital refueling. If Starship is refueled with just 1 tanker, it can get that GTO payload capacity right back up to 150,000 kilograms. And if you refuel it enough, it can actually take 150,000 kilograms all the way to the moon or Mars. That is game changing. Another huge upgrade for Starship is its massive payload bay. The Falcon 9 and Falcon Heavy share the same fairing, which is about 5 meters wide and 14 meters tall, with a total usable volume of 145 cubic meters. Although there is an extended version coming soon that is taller and will get the volume closer to 200 cubic meters. But Starship's payload bay is a whopping 9 meters wide and 18 meters high, with a usable volume of around 1,000 cubic meters. Yep, that's more pressurized volume than a 747. And there's an extended payload version coming soon that's 22 meters in height. Another big difference is what these rockets are made out of. The Falcon 9 is made out of 2219 aluminum alloy and some carbon composite, while Starship is made out of stainless steel 304L and will eventually be made out of a SpaceX in-house developed 30X stainless steel. Now, aluminum is typically the lighter option, but only really at cryogenic temperatures. But the reason for using stainless steel on Starship is because it not only needs to handle low cryogenic temperatures, but it also needs to handle re-entry heat for both stages. The Falcon 9 actually has some heat shielding on the octaweb, which is the bottom of the booster that holds all the engines. This keeps the extreme heat of re-entry from destroying the fuselage. Because of Starship's stainless steel construction, they're hoping to not require any additional heat shielding on the super heavy booster. But the upper stage of Starship will need to employ additional heat shielding tiles along its windward side or its belly when it's re-entering from orbital velocity. Now, we'll talk about this a little bit more in a second, but had they gone with another material, it would have required even bigger and heavier heat shielding. Originally, SpaceX wanted to use carbon fiber for Starship, but maybe one of the biggest reasons they switched to stainless steel is so they could rapidly prototype the vehicle. They can construct, make changes to, and iterate on a stainless steel Starship with simple construction methods and do it really cheap too. We're not really going to get into the philosophy of this iterative and quick design, building, manufacturing, and prototyping process in this video because we've covered it very much in depth in the SLS versus Starship video already. But maybe the most unique bit of hardware are those giant flippity flappity finny air brake things on Starship, or as I call them, ailerons. Now yes, these are something entirely new. They're a unique control scheme that will help the vehicle maintain control while re-entering belly first. These ailerons will basically be powered by some Tesla electric motors with a direct drive. Despite requiring insane amounts of torque, geared the right way, that's something an electric motor has plenty of. And they'll be powered by Tesla batteries too, or at least derived from them. And for longer missions, Starship will have solar panels. Now, we don't have too much info on that yet, but they'll definitely work their way into designs. But this is all just a giant iterative phase. SpaceX is making a huge and powerful rocket. But what's it all for? Forget the size of Starship. The economics of this rocket is probably the biggest thing. Now, we're not really going to get into this pricing too much because we've talked about that a lot in other videos, but I just wanted to talk about price kind of generally to help put into perspective how game-changing Starship could be. And of course, only time will tell what the true cost of everything actually will be. Despite being able to take almost 10 times as much payload into orbit as the Falcon 9, Starship should cost less than the Falcon 9 to launch. In fact, because it's fully reusable, it should basically only be the cost of fuel and personnel time. But we're talking about potentially way less than a Falcon 9. SpaceX is hoping it'll cost less to launch than their Falcon 1 even. I mean, in fact, it very well might end up being the cheapest ride to orbit, period. No matter the payload. In other words, it could be so cheap to launch an entire Starship that you could put just say a small sat or a couple of CubeSats or something tiny on it, and it might be cheaper than launching on say an Electron rocket or some other small sat launcher. And that, my friends, is why Starship is truly revolutionary compared to even the Falcon 9. But in order to fulfill that goal, Starship will have to be reusable. Fully and rapidly reusable. So just how exactly can it do that? What hardware is different that's going to make that dream happen? And now for the coolest part, or at least my favorite part, reuse. After all, there's nothing more exciting than watching a rocket land in person, falling from the sky, igniting its engines at what feels like the last possible second, and landing under a precise column of flames. And Starship is going to be taking this up a notch. After all, the Falcon 9 has set a new bar in the aerospace industry by propulsively landing the first stage and reusing it. As of the making of this video, nearly half of all Falcon 9s that have ever flown have used a booster that's flown more than once. And what SpaceX developed for the Falcon 9 and the Falcon Heavy's booster is clearly working out great. And it's actually a very similar method they'll use for the Super Heavy boosters. So let's follow the first stages and talk about all the systems and the hardware in play and how it all works. Of course, at liftoff, all engines will ignite on both rockets. As soon as the computer senses the engines are up and running smoothly and at full thrust, it'll command the launch pad to let go. Both rockets will ascend, mostly vertically at first, to get out of the thickest parts of the atmosphere as quickly as possible. But shortly after takeoff, they'll begin to pitch over horizontally in the direction of their desired orbit. By stage separation, they'll pretty much be entirely horizontal, giving the upper stage as much horizontal velocity as they can possibly spare. Let's assume both first stages are going to be heading back to the launch site, otherwise known as Return to Launch Site, or RTLS. The Falcon 9 only can do this for fairly lightweight low Earth orbit missions, but Super Heavy will likely always return to the launch site, like the actual launch complex, not a separate landing complex. In order to get back to the launch site, the boosters need to cancel out their horizontal velocity as quickly as possible, because at stage separation, they're traveling at thousands of kilometers an hour away from the launch pad. This is called the boost back burn. The Falcon 9 lights up 3 of its 9 Merlin engines, but Super Heavy will likely light up all of its center engines. Not only do they need to cancel out the horizontal velocity, they need to keep burning until they've actually completely reversed course, heading backwards from the original velocity, and make their ballistic trajectory end up at the landing site, or just short of the landing site for safety reasons. After the engines shut down, the boosters will be coasting back to the launch site. Seeing as they're well above 100 kilometers at this time, they have no air resistance to slow them down. So during this period, the cold gas thrusters on the Falcon 9 home in and precisely target the landing site using little tiny puffs of nitrogen. Starship will use its hot gas thrusters for any of these maneuvers. But the idea is basically the same. Small, tiny impulses can help precisely point and guide the booster back home. During this phase, they will deploy the grid fins, although in the vacuum of space, they obviously don't provide any control yet. So the boosters will follow their ballistic trajectory, and eventually they'll both begin to experience more and more of the Earth's atmospheric pressure. The air in front of the booster will heat up due to being compressed by the leading surface. Due to the laws of thermodynamics, as air is compressed, it's heated up. The air in the bow shock compresses so much it actually turns into a plasma. This plasma can be about half as hot as the surface of the sun. Here is where the Falcon 9 does something that Super Heavy is hoping to avoid. The Falcon 9 will again light up 3 of its 9 Merlin engines to slow itself down just as it begins to really experience those extreme atmospheric temperatures. This not only slows the booster down, but it also basically creates a force field in front of the booster, providing a boundary of exhaust gas which is a lot cooler than the plasma. Without this step, the Falcon 9 booster would likely not survive the re-entry process. After all, SpaceX tried to recover the Falcon 1 and Falcon 9 boosters using parachutes for the first few flights, which kept failing. By the time the booster was supposed to deploy the parachute, it was too late, because it's hard to deploy parachutes when you're in a million flaming pieces. But again, as we mentioned before, this is something that stainless steel should allow the Super Heavy booster to forego, which will save fuel and thereby increase overall performance. Because of its much higher melting point, Super Heavy is hoping to just grit its teeth through this process and survive this brutal regimen. And I think they can do it. I mean, after all, Rocket Lab's Electron rocket has survived this portion of flight that Peter Beck is calling the wall. And that rocket is made from carbon composite. So it's definitely possible, although comparing these two vehicles might not be too fair. From this point on, the grid fins have more and more control. Grid fins are basically just hundreds of small fins stacked side by side. This allows them to be tucked out of the airstream on ascent, and then they're deployed into an atmospheric cheese grater when coming back down. People often think the grid fins are just an air brake or something to help keep the center of pressure behind the center of mass. But really, they steer just like an all-moving control surface, like the stabilators on the tail of the F-16. The entire thing rotates around a central point to induce control. For grid fins, they can move opposite pairs in unison to provide pitch or yaw, and they can all move opposite their pair for roll. The grid fins now steer really hard and point the boosters back towards the landing site. They can even pitch in a way that creates lift along the booster's fuselage and help it translate even further over. I should probably point out that all of this is guided autonomously based on GPS and altitude and all of the other measurements that the rocket has to try and point itself at a precise target. So it's not like someone's sitting there steering this thing. By utilizing as much of the booster as possible to basically glide, it also allows the air to slow it down as much as possible, which requires less fuel for the final landing burn. Now, unlike ascent, where the air is fighting against the rocket, here the atmosphere is helping to remove energy. So eventually the booster will line itself up directly overhead of the landing site. At the last possible moment, they'll light up their engines. And in the case of the Falcon 9, this has to be extremely precisely timed. The nearly empty Falcon 9 booster, even when only one of its 9 Merlin engines is running at its minimum throttle setting, still has too much thrust to just hover. So they have to perform what's been called a hover slam, or a less astronaut-friendly term, a suicide burn. This is where you light up your engines as late as possible. So late you don't have a second chance. And because of the high thrust to weight ratio, they have to reach zero velocity right at zero altitude. Otherwise, the booster will end up going right back up. Starship's Super Heavy booster, on the other hand, will land using only its inner engines. These are the only engines that can gimbal, and eventually, they'll be the only ones that can deep throttle, which is necessary for soft propulsive landings. The outer ring of engines will someday be those booster variants of Raptor that are higher thrust, but they can't deep throttle and they're fixed in place with no ability to gimbal. Super Heavy could probably technically hover, but you really don't want to do that. After all, hovering is just 100% a waste of fuel. All the fuel spent to hover is literally getting you nowhere. It's best to do the burn as late as you can and with as much acceleration as you can. The shorter the burn, the more efficient. But the good news is Super Heavy has the option to do a slower, less efficient burn if they for some reason want it to. From here, the Falcon 9 lowers its landing legs, which are hydraulically pushed out and then locked into place. Super Heavy will probably not have to extend its landing legs because they'll likely be fixed. At least that's what we know right now. Once the rockets land, they of course shut down the engines and begin to lower the tank pressures to something safe enough for humans to approach. For the Falcon 9, once it's clear to proceed, a crew will actually go out there and pick it up by 2 cranes and lay it flat on its side on a trailer. From here, they'll take it back to a hangar where they'll do a bit of checkouts and refurbishment. The Merlin engines often need a good checkover and potential cleanouts because of that buildup of soot. The quickest turnaround to date is about 50 days before it can be reflown, although that time is decreasing quickly. But this will all hopefully be unnecessary someday for Super Heavy, since the plan will eventually be to just pick it back up and put it right back on the launch pad. And thanks to the reuseful nature of the Raptor engine and Methalox, this might become a reality someday. Or maybe it'll be similar to kicking the tires like a jetliner before each flight, doing a simple checkout before reflying. Hopefully. So now let's look at the upper stages of the Falcon 9 and Starship. SpaceX is already pursuing reuse beyond the first stage by catching and reusing the nose cone or fairings on the Falcon 9. SpaceX has even reused the same fairing 3 times already. And this is great considering that they cost several millions of dollars. It just makes sense. Their Wile E. Coyote scheme to catch them has been paying off. And even when they miss a catch, simply fishing them out of the water has proven worthwhile too. But despite all of these reuse efforts, the second stage itself is always discarded. After the Falcon 9 deploys its payload, it either does a deorbit burn and discards the upper stage in a pre-planned exclusion zone on Earth, or it kicks itself out into what's called a graveyard orbit. But here's where SpaceX is going absolute next level with Starship. I know I've been saying that a lot, but this is the hard part. Despite the upper stage being a smaller portion of the rocket, it's substantially harder, maybe even an order of magnitude harder to recover something going at orbital velocity compared to recovering a suborbital stage. This is the biggest paradigm shift that Starship is hoping to achieve. The hardest and most cumbersome problem is speed. Minimum orbital velocity is around 28,000 kilometers an hour. Yes, literally about 10 times faster than a bullet. This means things that are up in orbit are traveling 8 kilometers or 5 miles each and every second. So the booster imparts a decent amount of the sideways velocity, but a booster's maximum velocity is only about 1/3 to 1/4 the speed that the second stage reaches. Now you might be thinking, oh well, 3 or 4 times faster? Why is that any harder to return? Especially if it's smaller. A vehicle that's going 28,000 kilometers an hour needs to slow back down to pretty much 0 kilometers an hour to not smash into the ground. So that means all of that energy needs to be removed from the vehicle somehow. And again, just like when the atmosphere slowed the booster down, we can now use the atmosphere to slow the upper stage down too. The problem is, the temperature of the compressive heating in the bow shock of a vehicle doesn't increase linearly with speed. No, it's not like if you go twice as fast, the temperature gets twice as high. That'd be child's play. It's not even that heating goes up by velocity squared. So go twice as fast and the heating is 4 times as much. No. Re-entry heating goes up by the cube of velocity. So go twice as fast, create 8 times as much heat. Ouch. So since the upper stage is traveling at, say, 4 times faster than the first stage as it re-enters, it can experience up to 64 times as much heat. That's why recovering the upper stage is so stinking hard. Now you might be tempted to think, well, why don't you just slow down before you enter, and that way you could get back down to those same velocities and temperatures as the booster. Well, in order to slow back down using your rocket engines in the frictionless environment of space, it would require exactly as much energy as it did to get up to that speed in the first place. So that means you'd basically have to have as big of a rocket on orbit capable of slowing you down as the one that you took off with, which would of course mean that the rocket that would launch that rocket would need to be like 10 times bigger too. So the solution that SpaceX came up with for this problem was to use as much of Starship as possible to slow down in the atmosphere. So they will enter the atmosphere belly first, exposing as much cross-section of the vehicle into the wind stream as possible. This is why SpaceX's Starship will re-enter more like a skydiver, and it won't go in engines first like the Falcon 9, or at a 40-degree angle like the Space Shuttle. It'll basically be slamming on the brakes as much as possible. Although they can pitch and kind of create some lift to manage peak temperatures, in general, it has to use as much surface area to really just distribute that heat as much as possible and slow down as much as they can. Now, in order to do this, it needs to be able to control and maintain stability. That's exactly what those ailerons we talked about earlier are for. They change their drag to control pitch, yaw, and roll. Re-entering the atmosphere allows the vehicle to exchange all of that insane amount of kinetic energy it has for heat. Think of the atmosphere as a giant brake pad, which does the same thing. A brake pad exchanges kinetic energy through heat from friction. Only in this case, it's not air friction that causes the heat like we mentioned before. It's compression of the air in the bow shock that heats up the vehicle. And again, this is why they went with stainless steel, so it can survive re-entry intact. Now, SpaceX has done something brilliant here, something that the Space Shuttle did not have. They made uniform heat shield tiles, since, the whole Starship is basically just a giant cylinder, besides the nose where it tapers and those hinges and stuff. Now, this will make for way easier checkouts, easy production, and easy manufacturing. Now, we don't know a ton of specifics about the heat shield, other than they're likely to be an in-house variant of a material called Tough Rock, which touts high reusability by being able to handle high peak temperatures before ablating. Now, there might be some hot spots that'll ablate a little bit each launch, but because they're uniform, they should be easy to swap out and replace when they get low. And again, it's kind of just like a brake pad. Eventually, these tiles will be mechanically mounted, and likely done so by an automated robot for quick and easy manufacturing and replacement. And these heat shields might be one of the only things that really ever wears down and will require maintenance on the entire rocket, at least in a perfect world. Okay, so Starship eventually gets slowed down from going 10 times faster than a bullet to a relatively slow terminal velocity of maybe a couple 100 kilometers an hour, falling straight down now, but still belly first. And here's the thing that's going to be truly, absolutely insane to see. Starship will still need to land using its sea-level Raptor engines, and as you might recall, those engines are on the bottom of the rocket, which at this exact moment are facing sideways, completely horizontally. The solution to this? A wild, daring, and potentially hard to nail down belly flop to tail down maneuver. This maneuver will make the Falcon 9's landing look like a walk in the park. It's a maneuver that would probably make the best stunt pilots in the world poop their pants. The first attempts at this will look a little bit different than the eventual system because the cold gas thrusters on early prototypes aren't very powerful and can't aid too much in that flip maneuver. But for the initial prototype landings, the rear ailerons will tuck in to aid in the rotation and the 3 Raptors will light up while going horizontally. However, they'll be at maximum tilt, pitching the rocket's nose up as quickly as they can. Of course, in doing so, it's going to inject a heck of a lot of horizontal velocity. So in order to negate that and land on their target, it's going to need to overcorrect, swinging back over to the other side, canceling out the horizontal velocity before straightening out and touching down softly. And they're about to try this for the first time. And I'm sitting here wondering what's going to make me just lose my mind more. If they stick that landing, I think I'll lose my mind. But also if they just belly flop and blow up, well, regardless, whatever the outcome, it'll be spectacular. Eventually, on more production-ready and advanced versions, when they get to those hot gas thrusters, this maneuver should be able to be done completely by the gas thrusters and the ailerons. Then it'd just be a simple hover slam landing, just like a Falcon 9. This maneuver is extremely important because when you're trying to land a vehicle this size on Mars, there's no runway, there's no way you can glide and land on wheels. You have to nail this maneuver. This has to be easy peasy here on Earth and done over and over again before we put humans on it and then send them off to Mars. Now I should probably point out here another thing that we get asked about quite a bit, and that's the landing legs on Starship. For now, the landing legs are pretty small and tucked inside the skirt of Starship prototypes, but they'll eventually evolve and be upgraded quite a bit. After all, when it comes to landing on the moon or Mars, you may encounter some uneven ground or boulders, so these legs will someday be self-leveling, which, although we don't have too many details about right now, is probably one of the easiest technologies on Starship. I mean, come on. If a camper can do it, it can't be that hard. But there's one really big technology that will debut on Starship that will be required to get humans to Mars, and that's on-orbit refueling. Remember how we talked about how Starship didn't really necessarily have a huge payload capacity to geostationary transfer orbit because it has to lug around all of its dry mass? Well, Starship can make up for that by refueling in orbit. If this vehicle really is rapidly reusable and the Super Heavy booster can just land and grab a Starship tanker and launch again on the next orbit, this could be the most important technology. By refueling Starship on orbit, it would have an astonishing amount of Delta V and could easily get to the moon or Mars with fuel to spare. But something like this has never really been demonstrated, not at this scale and not with cryogenic propellants. But luckily, SpaceX has even gotten NASA invested in this effort. For now, it's a $53 million contract to study transferring cryogenic oxygen between the header tanks and the main tanks, but eventually they'll hopefully be interested in seeing Starship to Starship refueling too. But like I said at the top of this episode, there are some other variants that we might see someday, like versions that are just completely stripped down, maybe just a single or a few vacuum optimized Raptors capable of taking huge payloads out to the outer solar system. That would make sense because you're not going to be retrieving that stage. And don't forget about the lunar lander version of Starship that we've talked about a little bit. That too is its own stripped down version that will never have to re-enter. So they are kind of doing that a little bit, but even that vehicle will still need to be refueled on orbit. So all said and done, Starship takes reuse up the next level, potentially to Elon's ultimate goal of a rapidly reusable orbital rocket. As he says often, if you designed an expendable jetliner, you'd get laughed out of the room. So Starship could truly usher in a new era of spaceflight. Starship is simply a massively ambitious proposition, but there's few physical barriers which would make it impossible, other than it's never been done. And like anything that's never been done before, the unknowns are unknown. I fully expect Starship to have some stumbling blocks along the way and learn some valuable lessons too. There'll likely be many more explosions along the path to orbit, and even once operational. I mean, remember, the Falcon 9 hasn't always been smooth sailing either. Nothing is when you're pushing the boundaries either. But now the Falcon 9 is one of the most reliable and most flown rockets. What used to be an experimental landing is now expected and almost mundane. After all, Elon has said in the past that he hopes these landings become so routine that they're boring. And although I'm personally not quite to that point yet, it is getting close. So to summarize, Starship takes everything SpaceX learned from the Falcon 9 and upgrades it into a brand new super heavy lift rocket that's rapidly and fully reusable. It's going to be huge, the biggest and most powerful rocket ever made. They're utilizing methane that burns clean and is efficient. They developed the Raptor engine, which is a compact and efficient workhorse. They're scaling the vehicle up to a huge degree so they can pursue full reuse without sacrificing performance, and in fact, increasing performance. And perhaps most importantly, they're trying out new landing techniques that, despite being absolutely bonkers by design, should potentially solve the problem of surviving re-entry and land propulsively on a dime. We'll see lots of Starships. Starship tankers, Starship people carriers, Starship lunar versions, Starship cargo versions, etc., etc. And all of this is in pursuit of getting human beings to Mars, which, when you solve that, just so happens to make rockets a whole lot more capable and a whole lot cheaper here on Earth too. Starship will truly usher in a new era. And that is not hyperbole. So what do you think? Do you think Starship will live up to its ambitions? Do you think SpaceX will actually recover and reuse the entire rocket? Or do you think plans will change? Do you think this vehicle will actually take humans to Mars, or is it all just a giant pipe dream? Let me know your thoughts, or if you have any other questions in the comments below. But the good news is, if you have questions and you want to just dive into this more, I already have a ton of videos for you that go even deeper into a bunch of these topics. In fact, I put together a whole Starship playlist now that has videos like my interview with Elon about Starship, SLS versus Starship, the Raptor engine, why Starship won't have an abort system, why they're using stainless steel instead of carbon fiber, why Starship will belly flop, and a few others. Links to that playlist and each individual video is in the description below. Now be sure you're subscribed and stick around, because I'll be interviewing Elon Musk again here very soon, and I'm going to be sure and ask about all the upcoming changes in case we missed anything, and also kind of follow up on some of those things that I was a little bit vague about in this video because we just don't have those answers yet. So fingers crossed we don't get any huge surprises and it doesn't immediately just date this video. Please. And also in the description, you're going to see links for Casper Stanley's awesome work, including his awesome Rocket Explorer app. You guys have to check this out. It's available on Steam or coming really soon. It's kind of in the middle as I'm shooting this, but you can check it out. It is an awesome app that shows you different rockets and all these things. His renders are amazing, and you definitely have to be following him on Twitter because he has some of the coolest content. And another quick shout out to Eric Space on Twitter at ERCX Space, who provided a few of those awesome videos too. And I also owe thanks to Corey at CBass3D Productions, and that's at C_Bass3D on Twitter. Definitely follow his work too. I know there's sometimes huge gaps between my videos because I want the quality to be the best they possibly can be, and I can only do that because of the support of my Patreon supporters. If you want to help make what I do possible, head on over to patreon.com/everydayastronaut. There you'll gain access to exclusive live streams. You'll gain early access to scripts where you can give your input or ask questions about videos before they come out and help make these videos better. But you can also gain access to our exclusive subreddit and our exclusive Discord channel, which is just an awesome place to hang out. We have just the best community full of really fun people that we're all just learning together constantly. I hang out there all the time. So if you want to join our awesome community, head over to patreon.com/everydayastronaut. Thank you. And while you're online, you definitely need to check out our web store at everydayastronaut.com/shop, where you'll find shirts like this Future Martian Society shirt, which has a ton of nerdy details like I talked about. This shirt is just jam-packed. First off, the side has the gravity and the atmospheric composition of Mars, which I figured would be you know, since we're talking about Starship, which is going to Mars, definitely a fitting shirt. But there's way more to it than that. Because notice it says Arcadia Planatia on the little logo, and then it has some coordinates. Those are the exact landing coordinates of the proposed Candidate A landing site for Starship. So this way you can just show off how nerdy you are, because you're wearing a shirt that might have the first place humans are going to walk on Mars, the exact coordinates already printed out there for you. But don't forget to check out all of our other awesome stuff, like the full flow stage combustion cycle shirt and the brand new super awesome hoodie. We also have things like keychains and just tons of stuff. We're constantly making upgrades to the shop. So head on over to everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.